Hello everybody, Mr. Hendricks here. We're looking at equilibrium for our notes today. We have a question in Google Classroom. It's listed as question 4. So it has two parts to it. One, why are doorknobs located as far away from the door hinge as possible? And number 2, considering torque on a door, is there any way we can make it even easier to open the door? So please answer those questions. So number 1, we've talked about that in class before. Why are doorknobs located as far away from the door hinge as possible? And that is because of torque. So if we have a doorknob, so say we got our door, we have our doorknob all the way out here, we have hinges here and here. That's going to be making that easier. So let's do an overhead view here. So hinges here and door there, doorknob there, and there. So we have the hinges as far away from the door as we can, because then our torque, we have to apply less force. Because remember, torque is force times lever arm, or radius. If we have a longer radius, which is why we have the doorknobs out there, then the force will be less in order to pull on the door. Okay, so that'd be answer for part A, because it makes the force less and makes it easier to open the door. So part 2, considering torque on the door, is there any way we can make it even easier to open the door? Okay, well, yes, we could somehow increase our length of the radius for the torque. How would we do that? So you guys might have seen some of the doors they might have for people with disabilities. There might be a bar, some kind of a bar there off to the side, or this might be down a little bit further. Okay, so it makes it more accessible for people. It makes it easier to open the door. So now if we increase that lever arm, say we're going to be opening the door right there, that's going to make it even easier, so that'll make the force less because the radius or lever arm increased from here all the way out to here. So there are handicap accessible doorways for people that might have muscular or musculoskeletal issues. Okay, so next slide here. So this is what we're looking at in this lesson. So we're going to kind of look at some scenarios that involve stability, static equilibrium, and rotational reference frames. And then we'll understand that Earth's rotation determines tropical cyclones, how they rotate. Okay, so remember we talked about the Coriolis effect in class. Okay, so the question posed here, why are some vehicles more likely to roll over than others? Okay, so think about that a little bit. Why are some cars easier to fall over or rotate or roll over than others? If you didn't know that, Jeeps are, I think they're better now. Okay, if you didn't know that, some are more likely to roll over than others. Jeeps were ones, I think they're better now, but Jeeps were some kind of vehicle back in the day that had a higher rollover rate, and that is due to the center of mass in the design of the vehicle. Okay? So the center of mass determines how easy something can tip over or how easy the torque can be applied to something. Okay? So, talking about center of mass here. So, center of mass of an object is the point on which the object, or the point on the object that moves in the same way that a point particle would move. Okay? So, it's kind of a weird definition. Center of mass is basically the concentration of the mass of the object. So we draw a point on an object where the center of mass is. Okay, and then objects that move freely through space rotate about an axis that goes through their center of mass. So if you had a point on an object, which we're going to see here in a minute, then that would be the point that we draw rotating about the object. So let's consider this right here. So we have a dancer, okay, a ballerina, and the center of mass kind of right in the abdominal area there. If the dancer were to jump, okay, then we can draw a line through the center of mass which shows the path of the dancer. Okay, so that center of mass would be right there for first part, the second part would be right there, the third part would be right there. So that's what you would do for a motion diagram. You draw from the center of mass. Okay. So the next thing we're looking at is center of mass and stability. So we can read that bullet point there. Object is said to be stable if a large external force is required to tip it. So think about something like a bulldozer or heavy construction equipment. It takes quite a bit to tip over a bulldozer. So that would be a fairly stable object, right? That's going to have a very large center of mass that's going to be closer to the ground. Okay, so think about something maybe like a water bottle or something like that. It's a little bit smaller, a little bit easier to tip over. Okay, so that's going to be less stable. We could think of a box. Sometimes if you guys get packages in the mail, sometimes boxes are stable and sometimes boxes are really unstable and they just kind of tip over right away. So that's what we're going to look at for the next scenario here, is thinking about a box. Okay, so let's consider a box here. A box is stable as long as the direction of the torque due to its weight keeps it upright. So if I apply a force here, okay, that would cause a torque going counterclockwise. Then we could say that the center of mass is going to cause a torque that's going clockwise. All right. So for scenario A, we consider this stable. Let's say that the forces are balanced. So gravity from the box is going to keep me there, but that torque would balance that torque out and it's not going anywhere. Okay. So once we pull hard enough, that torque here, the torque of our applied force, is going to be a larger force than the torque due to gravity. Okay, and then we can see in scenario 3, once that box starts falling that way, then that gravitational force is not going to cause a torque that's holding it down anymore. Right? Once we get that center of mass beyond a certain point, then that center of mass will add to the torque that you're pulling with. Okay, so just kind of thinking about how stability works. If something is heavy enough to keep a torque from pulling it sideways, then it's considered stable. If something is not very heavy or the distribution of weight is off one side or another, then it's going to make it a little bit easier to fall over and less stable. So for instance, say we had the center of mass maybe was over here. Once that torque gets that pulling that way, or maybe even down here, once that torque or that force starts pulling that way, then this is going to switch directions and it's going to be pulling the box down, right? So let's think about vehicles, how vehicles are made rather than boxes now. So we have a car and a van, and the car center of mass is there, the van center of mass is there. So if we compare the two, the van has a higher center of mass than the car, right? So let's think about turning a corner or starting to, like on an embankment or something like that, we're turning a sharp corner. Which one would be the better option here? Would it be the car or would it be the van? Well, let's kind of look at our distribution of weight here. So center of mass is right there, okay? And then center of mass is right there. So if we were thinking about that, once that center of mass gets beyond a certain angle, then it starts to torque that way, right? So starting out, if we have a force going that way, so then this center of mass would keep me in place and hold me down, right? So this center of mass right there, same kind of idea. So when you're turning a corner, there is a force applied this direction, okay, due to gravity, because we kind of break down gravitational components. Gravity is going to be pulling on that center of mass, and at some point in time, if you're turning an extremely sharp corner, the vehicle could tip over. Now, thinking about Jeeps, okay, so let's say that this is my Jeep. I got my rollover bars or something there, and we're looking at the back side of the Jeep. Wheels there. It's a pretty terribly drawn Jeep. Jeeps had a center of mass that were higher, okay, because they had a heavy frame, and usually the wheels are a little bit bigger, okay, because it's made for off-road terrain. Okay, the frame is really heavy, but normally the center of mass is higher. So these are built for going off terrain, but if you turn a sharp corner with a Jeep, then that centripetal force, that centripetal acceleration on that center of mass can cause it to roll over. Okay, so say we're turning this corner here, then that center of mass would feel a pull due to that centripetal acceleration and could roll over. So there's some other vehicles besides Jeeps too that have a higher center of mass. Generally, you don't want, for vehicles, you don't want something that's high off the ground or a narrow wheelbase. If you have a wider wheelbase and closer to the ground, then it's more stable, right? The weight is distributed so it's more stable. Okay, so here are some conditions for equilibrium. So this is kind of like when we're looking at systems, how can we define that they are in equilibrium? So static equilibrium is a term that we're going to be kind of looking at. So think about static. Static means not moving. So static equilibrium is if both its velocity and so it's normal linear velocity and angular velocity are zero or constant. Okay, so these velocities can be zero or constant. So there is no acceleration there. Okay, so first transitional equilibrium. Okay, or So first, translational equilibrium. So think about what translations are. That's left and right movement. Okay, that is the net force exerted on the object must be zero. So there is no net force in this situation or in this scenario. Net force is equal to zero. Okay, so second, it must be in rotational equilibrium. That is, net torque is zero on the object. So for something to be in static equilibrium, we got to have translational equilibrium, so net forces are zero, and we got to have rotational equilibrium, so that's net torque equals zero. So that we have our net force and net torque, both of those have to be zero in order for it to be in static equilibrium. Okay, so let's look at a scenario where we have static equilibrium right here. So in order for something to be considered in static equilibrium, well, first, in general, equilibrium is where there is balanced forces in the system. Okay, so the scenario we're looking at would be this ladder that's sitting on sawhorses here. So there is no rotation going on, so that means there is no angular velocity or there's no angular acceleration. And the whole system, the whole thing is not moving at all, so there's no linear velocity. So in order for something to be considered static equilibrium, the system can't be moving with a velocity in general, and it can't be moving with any angular velocity. So this is a static equilibrium problem that we're looking at solving forces and torque. Okay, so it's a 5.8 kilogram ladder that's 1.8 meters long, resting on two sawhorses. Sawhorse A, which would be this one, is 0.6 meters from the end of the ladder, and sawhorse B, right there, is 0.15 meters from the other end of the ladder. So we can see the radii or the distances drawn here in the diagram. What force does each sawhorse exert on the ladder? Okay, so we're trying to find the force due to this sawhorse and the force due to that sawhorse. So then we have to kind of look at what forces are acting in the system. So this diagram right here shows us kind of a force diagram or a free body diagram, I suppose, of the forces acting on the ladder. All right, and then down below here, that last diagram kind of shows us what we want to pick for an axis of rotation to kind of solve the problem. Okay, so when we're working through these problems here, it's going to be helpful to make an equation with net forces, and then when we actually start to figure out all the torques and stuff going on, we have to pick a point of rotation. So this diagram is going to help us out, kind of tells us to pick this as our axis of rotation, and we'll talk about that here in a minute, but that's what's going to allow us to find all the forces going on here. All right, so let's write our net force equation here. So net force, so that would be all the forces in the system. Right now, nothing is moving, so our net force is 0 newtons. But we can break this down to say, well, what are all the forces that we add together that would give us 0? Well, we're going to have the force of A, and if we're using the diagram over here, A is going up, so let's say up is positive, down is negative. So force of A is going up, and we're going to have force of B going up, so those are going to add together. And then we have force of gravity, that's on that ladder, that's going down, so we will subtract that. Okay. Now we're going to need this equation here again in a little bit. We can make this a little bit nicer. We can just say our positive ones are there as a force of A plus force of B. That's going to be equal to the force of gravity on that ladder, which that makes sense because A and B, the sawhorses, are holding that ladder up. Okay. Let's list our variables. So we have mass of the ladder. Okay. That's 5.8 kilograms. We got G, that's gravity, that's 9.8 meters per second squared. All right, and then really we're going to have to kind of go from here. We got to think about torques in the system. So in order for us to find this, so really the only thing that we have in this equation here is force of gravity on the ladder, which we can find that. So let's do that quick. Okay, so force due to gravity is mass times gravity. So our 5.8 kilograms times 9.8 meters per second squared. Okay, so I'll just write those in there, and that's going to give us newtons. So our ladder will have 57.82 newtons acting on it. So that's the weight or the force of gravity on the ladder. So that would go right there. Right, so we can plug that in if we want to right here. So force of A plus force of B, that's going to be 57.82 newtons. Now, we don't know A and we don't know B. So we got two unknowns. So we got to figure out what to do next. Okay? Well, we know that if we take out one of these sawhorses, that ladder is going to go down, right? That's going to tilt down. And if we took out B, then it would tilt down there. Okay, so there will be some torque involved in this scenario, and that's what we're going to have to use to figure out those forces. Okay, so if we think about the torques that are involved, A, right, if I had A there, that's going to be pushing up, so that's going to cause a torque that way. All right, this one, if I got rid of that, if I got rid of B, that'd be causing a torque that way. Okay, and then B, if I got rid of A, would technically be causing a torque that way. So let's think about all the torques in the system here. So we have torque of A, torque of the ladder, and then we have torque of B there. Okay? So we could kind of, in order for us to figure out our forces here, we can make one of these our axis of rotation, right? So if I have this as the axis of rotation A, as we have listed down below, then our two torques in the system would be that torque and that torque. Okay? So we'd have torque of the ladder would equal the torque of sawhorse B. And then we can go from there. If we think about torques, if I say that A is the axis of rotation, that's not really going to have any torque, right? Because if you had like our two people sitting on a sawhorse, something like that, we just calculated the torque of this person and the torque of this person. We didn't really have to think about the lever or the fulcrum that it was sitting on. Okay, so we're going to declare A as our axis of rotation, and that's going to make it quite a bit easier. So let's say that A is our rotation. The only torques that we have involved here will be the torque of the ladder and the torque of that sawhorse there. So let's say that torque of the ladder is equal to torque of sawhorse B. Okay, so then we can kind of break this up. But what's your equation for torque? It's force times radius. So force of the ladder, force of that ladder times radius of the ladder is equal to force of sawhorse B times radius of sawhorse B. Okay, so the radii or the radiuses in here are what kind of lose people a little bit. We know the force of the ladder is 57.82, right? So 57.82, and then our radius of the ladder. So these, the radii here, we have to consider from the axis of rotation. So we said that A is going to be where we're rotating from, okay? So, right, if we took this out, if we took B out of there, then the ladder would just fall down, right? But now B is there holding it up. So we always go from the center of mass when we're talking about these. So from A, where is the center of mass of the ladder? That's going to be right here. So what's my radius? That's that 0.3 meters, okay? And then we have force of B, which we don't know. We can find it. And we need the radius of B. So again, how far from my axis of rotation is that? So we got all the way over here. So how far from A is B? So we got 0.30 plus 0.75. So let's write that up here. So radius of B is going to be 0.30 plus 0.75. Okay. Well, that's going to be 1.05. Okay, because right, 0.3 plus 0.7 would be 1, and then we got 1.05. So now we have enough information here just to find the force of B. So the force of sawhorse B. So let's do that. And we end up getting 16 0.52 newtons. Okay, so you have to multiply these two and then divide by 1.05, and you'll get 16.52 newtons. Okay, that's the sawhorse B. Now we have this equation that we made before, our force equation. We can use that to figure out the force of A. Okay, that's probably the best way to do it. Come back here. The force of A plus 16.52 newtons equals 57.82 newtons. And we just minus, oops, forgot my decimal there, minus 16.52 newtons from both sides. And we get the force of A is 41.3. Okay. So those are the two forces involved acting on that sawhorse. Okay, if we look at all three of the forces, just so we can kind of check our answer, we have the force of gravity, which is 57.82, force of sawhorse A, 41.3, force of sawhorse B, 16.52. If you put all those into your equation here, we should end up getting 0. Okay, the only reason we might not get 0 is if we rounded kind of wrong, but it should be close to 0. Okay, so that's how that works for those. So we need to think about our net force, make a force equation. Okay, so this is the force equation that we got to down there. And then we need to kind of pick an axis of rotation in our diagram. So we chose A, and we chose A because that got rid of one of these variables, right? Because if we just chose the center, we knew both pieces of information. We knew force and radius for that ladder, so we wouldn't want to get rid of that because we knew everything. Okay, so that's why we chose A, because we had everything known, one unknown here. Okay, so let's look at another example here. All right, suppose the person lifts the end of the ladder that's nearest to sawhorse B. What force would the person have to exert? What force would the remaining sawhorse exert? Okay, so we got our sawhorse again, or our ladder. This is sawhorse A, and then this is sawhorse B, and then we have a person now lifting that from the end. Okay, so we got gravity there, and those are not perfectly equal. I probably should have drawn them off to the side a little bit. Okay, let's kind of extend this side so it looks a little bit similar to the top. Okay, so we have this person lifting from this end here. All right, so let's list all the forces involved here. So that person is lifting up. All right, so let's draw kind of a diagram on the ladder here. So we have sawhorse A that's pushing up, gravity on the ladder pushing down. Now, is there going to be a force for sawhorse B if this person is lifting it up? No, there will not be, because this person is going to be lifting it off of the sawhorse, so there is no force for sawhorse B, but there is the force of the person there. So force of the person, force of gravity, and force of sawhorse A. So if we think about a net force equation here, again, we're going to say that everything is in equilibrium, so net force is 0. So we're going to have force of sawhorse A plus force of the person, because those are the two that are acting up, minus force of gravity, and that will be equal to 0. Okay, so we have our force equation here. And now we're going to have to pick or figure out torques in the scenario, because we can't just use the variables we had from above, because this person's, like the radius of that of B changed. We have now this guy way out here, so that's going to change our torques involved. Okay, so let's say we're going to pick, let's say we pick A again as our point of rotation. Then if we think about torques involved, we're going to have the torque of the ladder is equal to torque on the person. So the person is lifting up this way, and ladder is going down that way. Okay, so those should be equal and opposite torques. So we have force of the ladder times radius of the ladder is equal to force of the person times the radius of the person. And now we might need to scroll up to look for these again, but we know force of the ladder is 57.82. Okay, and the radius of the ladder was at 0.3. equal to force of the person times radius of the person. So let's scroll up and see if we can pick out what our radius of the person is going to be. So we were going from here all the way out to here now. So we got 0.3 plus 0.75. Well, we did that already. That was 1.05, right? Plus 0.15. So we'd add 0.15 to that because we have all the way out to here. So the radius of that person is going to be 1.2. Okay, so 1.2. So multiply these, divide both sides by 1.2, and we get the force of the person to be 14.46 newtons. Okay, so that is the force that the person has to exert to lift that up. Okay, so that would be the answer there, the force the person would have to exert. So in the second part, what force would the remaining sawhorse have to exert? So that means we're going to have to use our equation here, and we're going to solve for A. So let's plug everything in, see if we can solve for A. So force of A plus that 14.46, that's the force of the person, minus force of gravity, which is 57.82 on the ladder, is equal to 0. Okay, so we'll have to put these together. So force of A minus 43.38 equals 0. Move the 43.38 over. And then we get the force of A is equal to 43.38 newtons. Okay, so again, just like up above, we could plug this in, we could plug this in, and we could plug this in. Those are our three forces. We could plug those into our equation up above, right there, and we should get 0 out of the deal. Okay, so there's a couple of problems involving static equilibrium and torque. So let's look at one more here. So if you wanted to, you could pause the video, see if you can work through this. This one is kind of set up to take you through step by step with ABCD. So see if you can figure it out. All right, so for part A, so let's read the problem here quick. 7.3 kilogram ladder, 1.92 meters long, resting on 2 sawhorses. Again, we got a diagram here. It's kind of nice. We have all the radii or all the chunks there shown. Sawhorse A is on the left, located 0.3 meters from the end. Sawhorse B on the right, 0.45 meters from the other end. Choose the axis of rotation to be the center of mass of the ladder. Okay, so this is where we want to have our axis of rotation right there. Okay, that might change it a little bit. So what are the torques acting on the ladder if this is our axis of rotation? All right, well, we're going to have torque of A and torque of B. Those are the two torques that are going to be acting on the ladder there, because our axis of rotation is that center of mass. Okay, so we could write out a little equation here just to say what our torques are going on. So our torque of A is going to be equal to torque of B, and A would be giving a clockwise torque there. B would be giving a counterclockwise torque, but they will be equal and opposite because this is in static equilibrium. And then that would give us, so we break this apart, force of A times the radius of A. So we are 0.66 meters from that axis of rotation, equal to force of B, and the radius for B is 0.51 meters from that axis of rotation. Okay, so this one's going to be going clockwise, that's going to be going counterclockwise. Those are the two torques in the scenario. So for part B, write in it the equation for rotational equilibrium. Okay, and that's pretty much what we did here. Okay, so we could take this one, we could say that this is our equation for rotational equilibrium. Those are the torques in the scenario that will be balanced out. Okay, C, solve for equation or solve an equation for F sub A in terms of F sub G. So before, I'm going to go back up here. So I'm going to write some variables here because I'm going to scroll down so we can have more room below there. So we have a mass of 7.3 kilograms. And let's move this down a little bit. That way we can scroll down and kind of look at our torque still. So everything else is in the diagram. So let's scroll down so we have some room. So C, solve the equation for F sub A in terms of F sub G. So what that is asking, that's asking for a net force equation. Okay, so our net force is 0, and we have 3 forces acting. We have that force pushing up, that force pushing down, that force pushing. All right, so our net forces here, we have okay, so the forces we have acting in this scenario is force of sawhorse A, and we're going to add force of sawhorse B because those are both in the same direction. They're positive because they're going up, and then we have minus that force due to gravity on the ladder. That is set equal to 0. Okay, so we can solve for F sub A. Okay, and that'll help us figure out our force of A. So let's say F sub A. So we would move this over and move that over. So it would be F sub G minus F sub B, right? Because we'd add F sub G to both sides. And then we minus F sub B to both sides. And we get that. Okay? So do we know force of gravity? Yes, because we have a mass of the ladder. So F sub G is equal to 7.3 times 9.8, which gives us 71.54 newtons. So that's F sub G, which we could plug in there in a little bit if we want to. All right. So I think for this one, we want to finish this and solve it. So let's find F sub A. We're going to find force of A in this scenario. So we're going to have to do like we did before. So we're going to have to use these two equations. So this one here, this is our rotational equilibrium equation, our torque equation. And then we're going to have to use this one here to solve. So let's put our force in there. So F sub A is equal to 71.54 minus force of B. So what's nice about this is we have it solved in terms, or for F sub A, and we could take that and plug it into our equation up here. So let's do that. So F sub A is 71.54 minus F sub B. Okay, I plug that in for there, right there, times 0.66 meters. Oops, let's just get rid of that meter there since I kind of, we're going to be getting newtons here in the end because we're looking for a force. Okay, so F sub B times 0.51 meters. And I probably could have written those the other way around. It'd look a little bit nicer. So 0.51 F sub B, kind of like that. Okay, let's move that down. Right there. Okay, so now we're going to have to solve this. So this is some pretty basic algebra here. That's distribute to there, distributes to there, and we get 47.22 minus 0.66 F sub B equal 0.51 F sub B. So now we want to get the variables on the same side, so move this over. Okay, and we get 47.22 equals 1.17 F sub B. And then we'll have to divide both sides by 1.17, okay, to get rid of that number in front of F sub B. So divide 1.17 And we get force of B is equal to 40.36. All right, so now we were looking for A, so now we're going to have to take that and plug it in. So F sub A, so force of A is equal to 71.54 minus 40.36. So force of A is 31.18 newtons. Okay, so we have force of sawhorse B, force of sawhorse A, force of gravity. If we added those three together, as in our equation up here above, we would show that they all add together and give us a net force of 0 because this is in equilibrium. Okay, so the last question here, how would the forces exerted by the two sawhorses change if A were moved very close to but not directly under the center of mass? So let's say we take A and we put it here. And we take it out of there. So what happens if we move sawhorse A there? Okay. Well, since this is really close to the center of mass, sawhorse A would be taking most of the force. Now, we don't know where it's exactly moved to, so we're just kind of predicting here. Like, we can't get any numbers for this question, but A would be taking most of the force, and B would have quite a bit less force on it. Right? So B had more force here right now because A is actually further away, so A would have less force, right? So these would kind of flip-flop. A would have quite a bit more force than B, since A would be closer to the center of mass. Okay? So these are some problems involving static equilibrium. Hopefully they make sense. So when we're looking at rotational frames of reference, so things that are rotating, Newton's laws are valid only for only in inertial or non-accelerated frames. Okay, so that kind of goes back to our static equilibrium idea. The objects are not accelerating. Velocity would be constant. If we have some acceleration involved, then we can't say that there is static equilibrium, or we can't say that there is equilibrium in that scenario, and Newton's laws won't work very well for us. Okay. So Newton's laws would not apply in rotating frames of reference as they're accelerated frames. Okay, so anything going in a circle is accelerating because definition of acceleration is change in velocity. Okay, so anytime you have a changing velocity, then you have acceleration. Okay, so they would not apply in rotating frames of reference. So we have a diagram down below kind of to look at to explain that. So let's consider this diagram down here. Okay, so we have someone standing in a center throwing a ball out towards an outside edge of a turntable. Okay, so if you are person A here, sitting on the ground watching the person throw the ball, then that ball is going to seem like it goes fairly straight off the turntable, right? The person's going to throw it, and it's going to bounce, bounce, bounce off the edge of the turntable. Now, if you're sitting on the turntable and that person throws that ball, then you're going to see that ball look like it curves a little bit. Okay, so this is kind of interesting because if the turntable is going here, you're sitting on it, that ball is going to appear to curve off to the side. But if you're out here, then the ball is going to appear to go straight. Okay, so scenario A, this would be called the ground frame or ground frame of reference. That would be like a straight path. And then scenario B would be like your rotating frame. So then we're going to have to think about, well, what would actually cause that ball to turn that way? He threw it straight that way, right? So what causes it to turn that way? Well, there's going to be a couple things involved, but it's really the Coriolis effect is going to be observed if you're sitting on there because of that rotation of the turntable there, right? So the Coriolis effect is kind of a fictitious force. So if anything, any frame of reference involves a fictitious force, okay, and we're going to talk about those on the next slide, then that would be something where Newton's laws do not apply, okay? So those would be accelerated frames. So let's think about our fictitious forces that we've talked about so far. Centrifugal force. I hope you remember this. So the centrifugal force is an apparent force that seems to push an object outward and observed only in rotating frames of reference. So that was if we had, say, you're in a car. Okay, I'm just going to draw a person. So the centrifugal force. So the centrifugal force, say that you are in a car. Okay, I'm not going to draw the whole car, but we're turning this way in the car. Okay, say you're going around a corner or something like that. What is your body going to feel? Well, your body's going to feel some kind of a force that pulls you out that way, right? Now, we talked about that before. It's not really a force, right? It's just an absence of a balancing force, absence of something holding you in place, right? So normally centripetal or circular motion involves tension of something. It involves friction or gravity. So that would be what's holding you in place, and there is no force pulling you outward, okay? So that is the lack of the holding force. So centrifugal force, anything that is involved that involves a centrifugal force is not going to be following Newton's laws, okay? The second part, or second thing we've talked about here before is the Coriolis effect, and now we're going to call it the Coriolis force, okay, because we're talking about fictitious forces. Okay, it's an apparent force that seems to deflect a moving object from its path. So if we were throwing something, say we shoot a cannon from the equator, then that object is going to appear to go that way, right? Because the Earth is rotating. So since the Earth is rotating, if we look at that object, it's going to kind of veer off that way. Okay, so an observer on Earth sees the Coriolis force cause a projectile fired due north to deflect to the right of the intended target. Okay, that's just a way, because of the way the Earth is rotating. If we were firing south, then it would deflect that way, right? So it's going to kind of curve due to that Coriolis quote-unquote force. All right, that's a fictitious force. Okay, so talking about Coriolis effect or Coriolis force again, direction of winds around high and low pressure areas result from the Coriolis force. So winds always go from high to low pressure, but we talked about the Coriolis effect and the Coriolis forces in class. Okay, so if we have a cyclone or something up here, it's going to appear to go counterclockwise just because of the way the Earth is rotating. So our cyclones would go in a counterclockwise motion up here, and then in the southern hemisphere they would follow a clockwise rotation due to the Earth's rotation. So the further you get away from the axis, technically the slower we're going. So the object is going the fastest rotationally right here, and then the slower here, okay? So then it's going to be going in a counterclockwise motion. All right, so those two pieces there emphasize that. So winds rotate counterclockwise in the north, and they rotate clockwise in the south, okay? And then we had a question before, what happens on the equator? Oops. Okay, so hurricanes and cyclones don't actually form right on the equator, and we have something that we've calculated within 4 degrees of the equator because of the Coriolis effect, and it's just too small. Okay, so you can look that up if you want to, kind of interesting, but they're either north of the equator or south of the equator, then they rotate as talked about above. Okay, so here are some questions you might want to look at, kind of think about them. So question 1, which is the point of an object that moves in the same way that a point particle would move? Okay, think about it. That would be the center of mass. Okay. Which best describes the state of an object, which its velocity and angular velocity are both 0 or constant? Okay, let's read through those. That object is in static equilibrium. Okay. And then down here, which is an apparent force that seems to push an object outward and is observed only in rotating frames of reference. Okay, it's pushing an object outward. They have a Coriolis, centrifugal, net, or normal. That's going to be the centrifugal force. Okay. So your assignment here is on page 204, 37 through 40. I will attach another video just going through those examples. If you wanted to look at it, I think one of the problems is on there. I think number 38 is on there if you wanted to check that out for help. So let me know if you have any questions. Hopefully this makes sense. Have a good one.